a single server, so one worker, one server. Poisson arrival or exponential interarrival time, so we have M here. However, the time to serve a customer is arbitrary. So it's not a exponential distributed random variable. So therefore we have G here for some general distributions. It could be uniform distributed, normal distributed, the service time. So again, we have one worker, and the usual first come, first serve, and the system can have an infinite number of people there, and customers can come from anywhere. Okay? So therefore we have the so-called MG1 model. So from last time, the lambda is the arrival rate of customers. So 5 customers per hour coming. Mu is our so-called service rate. So this is, for example, our server can process 7 customers an hour. And then sigma here is the standard deviation of the service time. So in terms of the quantities that we compute from last time, so we have WQ, which is the expected wait time in the queue. W is the expected time you spend in the store or system. L is the expected number of customers in the system or store, and LQ is the expected number of customers in the queue. Okay? So in this particular model, we can compute P0, which is the probability of no customers there. We can compute these quantities here, L, LQ, W, WQ, but there's no nice formula for calculating the probability of Pn, which is the probability that there are n customers in the system. Again, for steady state to occur, the arrival rate lambda has to be smaller than the service rate mu. Right? So basically, the worker has to work faster than customers coming. So the probability that there are no customer in the system, P0, is the same as the MM1 model, 1 minus lambda over mu. However, the LQ formula is different. Okay? So this is the expected number of customers in line. And sigma squared here is the variance of the service time. Again, the probability, you're interested in calculating the probability a customer coming will have to wait. That is defined as PW from last time. And again, because you only have one worker, the only time you don't have to wait is when there's nobody there. So the probability you have to wait is 1 minus P0. Then, as from last week, once you have LQ, you can use Little's formulas to calculate the other 3, right? So given LQ, you can use this formula to calculate WQ, and then you have WQ, you can use this formula to get W, and if you have LQ, you can use this formula to calculate L. If the service time is constant or deterministic, so the time to serve your customer, say exactly 7 minutes, then the model becomes MD1, D for deterministic. All the formulas are the same, except for the fact that in LQ here, the variance is 0. Okay, sigma squared is 0, and so LQ simplifies to simply this. Okay, so here a manufacturing company has a parts washing station that operates with one machine. Parts arrive at a rate of 4 parts per hour, assumed to be Poisson distributed. The time to wash or clean a part is constant and equals 10 minutes. So basically, part goes in, press the red button, 10 minutes later, boom, it's done, right? So what is the expected number of parts hanging around this washing station? Okay, so here our model is MD1 because Poisson arrival, but the time to serve a customer is deterministic because it's exactly equal to 10 minutes, and we have one wash. And the first come, first serve, infinite. So that's our model here. So what is the expected number of parts in the station? So that is basically just L, expected number of customers in the system. So to calculate L, we can use this formula here. So it requires us to first calculate LQ. And so we can use this formula to calculate LQ. So we use this formula here because it's the MD1 model here that we have. So we calculate LQ and we use it to calculate L. So the arrival rate is given. So we're told it's 4 parts per hour is coming. And then it takes 10 minutes to clean the part. And so that equates to a service rate or mute of 60 divided by 10. So I can process 6 parts per hour or clean 6 parts per hour. So I learned today that the wait list for this course in May has gone up to 60. That's practically a whole new class that we need to add. So they're thinking about whether they would add or not. Most likely they'll have to. Okay. So again, we will now calculate the LQ. So their formula over here is L over square and 2, 1 minus lambda over mu. Okay, so lambda is 4 and mu is 6. So LQ works out to be 2 over 3. Well, I remember about 3 years ago, we had a sudden surge of first year students. Normally it hovers around 520, 530, 540 maybe, but that 1 or 2 years went up to like 550, 560. So I guess we must be seeing the effects now as 3 years later. But this last September, it's gone back down to the 515, 520. Okay, so now that we have that, we are going to use this little formula here to calculate L. So whenever you go around this washing area, you see 1.33 parts lying around. After being here for a while, I like the 500s. Seems to work well. Rotman, they're in about 800 students, and it gets messy. You have to have so many sections, and you have several instructors teaching the same term, same course. So it just gets a little more messy. Okay, how about part B then? What is the expected amount of time a part spends in the system? So that is basically W, expected time spent in the system for a customer. And so we got L, Q, and L. So it's easily that we can use this formula here to calculate W. Okay, so basically we need to calculate W. And so we're just going to use the fact that L is equal to lambda W. L is 8 over 6. Lambda is 4. And so solving, I get W is equal to 1/3, which is 20 minutes. Okay, part C over here. Okay, it says suppose the time to wash a part is not constant 10 minutes anymore, but now it's a uniform distributed random variable and can take anywhere from 6 to 10 minutes. And so what is the expected number of parts waiting to get washed. And recall from your MGB11 or uniform distributed random variable, the mean is half of a plus b, and the variance is of the variable is b minus a squared over 12, where a is the smallest value the variable can take on, and b is the largest value the variable can take on. Okay. So we want to calculate expected number of parts waiting to get washed, and so in terms of our terminology, that is just LQ, expected number of customers in Q. Okay. So, and then we so we have this LQ formula here to calculate that. Okay, so for part C, our model is no longer MD1, it is now MG1, because it's not deterministic and it's not exponential either, so it's just some other kind of probability distribution. Okay, arrival is the same, 4 parts, but the service time is now changed. So we define X as the time to clean the part. And we're told it's basically uniform distributed. And can be anywhere from 6 to 8 minutes, 6 to 10 minutes. So next we calculate the average or the mean time to clean a part then. And from the formula on the handout, that is EX. And so it's A plus B over 2. And in this problem here, for us, A is the 6 and B is the 10. Okay, so 6 plus 10 divided by 2 gives us 8 minutes. So on average, it takes 8 minutes to clean, not the 10 as before in part 8. Okay, next, so therefore our service rate is then 60 over 8 gives us 7.5 parts per hour. So we can clean 7.5 parts per hour. Okay, next we calculate the variance of the time to clean the part, or so-called var x. And from the formula on the handout, that is b minus a squared over 12. Okay, so everything, the rates and arrival rates and service in terms of hours. So what I'm going to do is I'll convert the 6 minutes and 10 minutes into hours as well by dividing by 60. So we have 10 over 60 minus 6 over 60. So this gives me 1 over 2700, and this is my so-called sigma square, right? Okay, so now we're ready to calculate what we need, which is the LQ, expected number of parts waiting to get clean. And from my formula, there it is right here. Okay, so again, lambda is 4, and this variance, all this hard work to get it, 1 over 2700. Okay, so works out to be 0.319 parts. So whenever you go to this washing area, there'd be roughly 0.32 parts waiting to get washed. Well, so you might recall for your midterm, there was 6 questions, and the last one on this kind of, the last question was a killer, right? It was a financial planning question, but kind of in disguise, I suppose. So I have something similar ready for them in May, but over the weekend I have a change of heart, and I decided to remove that hard question and replace it with something a little bit more straightforward. Well, I think I'm not going to bother with putting out tricky questions. You're the last batch that's going to get a tricky question from me. Figure I'll just keep it straightforward. That way I don't have to, curve the grades, add 6 points, just make work for me, It's like, keep it hard, now I gotta add 6 marks. I add all the things, okay. Okay, so let's look at the next model here. Okay, in this next model, we have multiple workers, so K number of servers. Poisson arrival or exponential interarrival time, so M there. Arbitrarily service time, so not exponential time to complete service, so again the G. But there's no lineups permitted. Okay? When all the workers are busy, we don't take in customers. Okay? So therefore, the maximum number of customers that can be in the system is also K, the number of workers you have, right? Basically, customers are rejected when all the K servers are busy. And so again, the max number of customers that can be in the system N is just also K. A queuing system with no queue is known as a Erlang loss system, named after the mathematician Erlang. The probability that N customers in the system is basically the probability that N out of the K workers are busy. The most important probability is PK, which is the probability that all your servers are busy. And then it is then the same as the probability that customers arriving will be blocked or denied access to the system. So here we have the probability for calculating the N number of customers in the system, where here K is the number of workers we have. The expected number of customers in the system L is given by this here, where PK is the probability that all your K workers are busy. When customers arrive, they just go straight to service. So the time they spend in the system is basically the time getting served, defined as 1 over mu. Since there's no waiting lines, there's no LQ or WQ in this model. Okay, Microdata Software Inc. has a toll-free 800 number for customers to place orders. Assume 12 calls per hour are made to this number, Poisson distributed. Each customer service rep can process 6 calls per hour. Currently, Microdata has 3 internal lines, each operated by a separate CSR. Calls received on the 800 numbers are transferred to one of these lines if they are available, otherwise the customer gets a busy signal. Microdata wants to be able to handle 90% of callers. Is the number of current lines adequate? If not, how many more lines are needed? Okay, so the depiction is that customers call in. We have 3 CSRs. And basically, they dial in some 800 number. However, no lineups are allowed. And if all the workers are busy, they just get a busy signal. Okay, and if they are lucky, they get a customer service rep and out they go. So the model here is Poisson arrival, some other general distribution service time, not exponential. We have 3 customer service reps. However, no lineups. And so maximum will be also 3, and customers come from anywhere. Okay, so that's by these 2 numbers matching, it indicates that there's no line because the most you have is 3 because you've got 3 workers in the system. Okay, so we have our arrival rate is 12 per hour. And we have our service rate. And that is 6 calls they can handle per hour. Okay, to determine whether we're able to handle 90% of the calls, we want to calculate the probability that we're going to reject a call. And basically, we're rejecting a call if there are 3 customers in the system, so P3. So according to the formula here, P3 is lambda over u to the 3, summation 0 to 3, and so on. So therefore, the formula for calculating P3 is lambda over mu to the power of 3 over k factorial. And in the bottom here, we've got this sum that goes from 0 to 3, and lambda over mu to I over I factorial. Okay, so let's simplify this a little bit here. So the top works out to be 8 over 6. So I is 0, so 12 over 6 then I becomes 1, then I becomes 2, finally I becomes 3, and this works out to be 0.2105. Okay, so this means that this 0.2105 means that 21% roughly calls rejected, and that only approximately 79% calls handled. So they're not achieving their 90% target, so you need more lines. Okay, so let's try adding one more line. So now the probability that you're going to reject call is not P3 but P4. The probability that there are 4 people there. Okay, and so the P4 then is 12 over 6, but now to the power of 4 over 4 factorial. And then we would have 0, 1, 2, 3, and 4 over here. And this works out to be 0.0952. So it looks to me like 1 minus 0.0952 is equal to 0.9048, or 90.48% calls handled. And so basically we need 4 lines. I got an email earlier today that Rotman has set up some kind of AI task force, a bunch of professors, and maybe 1 or 2 of their lab technicians, and to kind of, I guess, guide the school, or their school, on how to use AI to help professors with their research and teaching, and also at the same time, how to, I guess, maybe deal with how much AI the students should be using on their projects, assignments, and whatnot. Okay, next, microdata believes that 60% of callers don't call back when they get a busy signal, and hence they lose the sale. The company estimates that each customer will make a $150 purchase on average. So what is the average loss in revenue for the current situation for an 8-hour day? So first, we have to determine how many customers get the busy signal in an 8-hour day. So number of customers blocked. So we have an 8-hour day here, and we receive 12 calls per hour. And from the original 3 lines, the probability of blocking is 0.21 from original 3 lines. The probability of blocking is 0.21. And so for an 8-hour day, roughly 20 calls get the busy signal. Okay, so in the 8-hour day, roughly 20 calls get the busy signal. The reason why I mentioned that is I was looking through some of your assignment 4s, and they look AI generated to me for some reason. They're nicely drawn up in little bubbles. However, the numbers don't make sense. But the answer, the final expected profit is correct. So how do they get that number given the other numbers are wrong? Baffles me, and there was a few like that. For years I thought, okay, my assignments are pretty AI proof. I don't know how you would do it. What you would ask, how you would draw it. But now I'm not so sure. Okay, lost revenue. So 20 customers get the busy signal. 60% of them don't call back. Each one of them spends $150. So the loss is $18.18. I guess I was intrigued because over the weekend I had some dinner with some other family, and one of the person says, look, I uploaded this picture of myself and my other 2 karate or jiu-jitsu practice teammates, and I told the AI picture image generation to draw me a picture, but in Pokemon style, And so it did it pretty good, and it was like just minutes to create it. So it's incredible what it can do. Okay, so let's look at the next model here. Okay, in this next model, we have single server. So again, one worker. Okay. Poisson arrival, so M here. Back to exponential service time, so M here, okay, and one worker. However, we have a finite system capacity of N. So again, picture security guard close the door on the store when they see more than 50 people there. So there can never be more than 50 people, right? And also picture, a call center. They don't have unlimited queues. Right? They have certain phone lines that they buy from Bell or whoever it is, and the minute there's too many customers waiting on their phone lines, then you're going to get a busy signal when you call. Okay. So the system cannot exceed capital N number of customers. They are simply rejected, get the busy signal, whatever, if more than N is there. So therefore, the system can reach steady state even if customers are coming faster than they can handle, because they will just close the door or stop taking in customers. So we define rho as the ratio of arrival over service. And then the probability of no customers in the system, P0, is given by the top formula if rho is, or ratio is not 1, and if the ratio is 1, it's just 1 over n plus 1, where n is the maximum customers allowed. The probability of n customer in the system Pn is given by this. Expected number of customer in the system L is given by this if rho is not 1, and if it's 1, it's simply n over 2. Then, given the fact that we have L, we can use a revised version of Little's formula to calculate the other 3, right? So we have to adjust it for the fact that we close the door once we hit capital N customers. So once we have L, we can use it to get W. We can also use it to get WQ. And once we have LQ, we can get WQ here. Okay, so in this example, two one-man barber shops sit by side by Pacific Mall. Each can hold a maximum of 4 customers. And any potential customer who finds the shop full will not wait for a haircut. So they don't close the door, but customers don't go in. It has the same effect as closing the door. Barber 1 takes an average of 12 minutes, and Barber 2 takes an average of 5 minutes to cut hair. An average of 10 potential customers per hour arrive to Barber 1, and 12 per hour will arrive to Barber 2. Assuming that the number of arrivals is Poisson distributed and haircuts exponential, which barber shop will more likely to be full when you arrive for a haircut? Okay, so in this instance, our model here is exponential Poisson arrival, exponential haircut time, 1 barber, first come, first serve. However, we only allow a maximum in the system. So this is n equals 4, which is the maximum customer in store. Okay, so maybe we'll break it down into barber 1 and barber 2. Okay, so let's look at barber 1. So arrival rate is 10 per hour are coming. Service rate, they are taking 12 minutes to cut a hair. So that equates to a service rate of be able to cut 5 customers per hour. I think 12 minutes is pretty fair. Usually it takes about, I would say, 15 to 20 minutes. Okay, next we calculate this ratio rho here, which is lambda over mu. So that's 10 over 5. Or 2. Okay, next we calculate P0. And since ratio is not 1, so we use this top formula over here. So rho is 2. And capital N for us is this maximum 4 here. And so we get P0 is equal to 1 over 31. Finally, we want to calculate the probability they're full, and they're full if 4 customers are there. And again, the Pn formula is rho to the power n p0. So that's rho to the 4 times p0. And rho is 2, p0 is 1 over 31. So the probability works out to be 5161 here for Barber 1. Okay, for Barber 2, arrival is 12 are coming. And then Barber 2 is really fast. They only take 5 minutes to cut a hair. And so the service rate is able to cut 12 customers per hour. Two months ago, 3 months ago. Anyway, we had some, event here, and brought some people from IBM, and they were talking about AI and how some companies can protect themselves, I guess, from AI attacks and so on. And it was one of the people there was like some chief scientist at IBM in this area, and this thing is he stood up there and he goes, basically, there's no intelligence. It's the wrong name, artificial. It goes, there's no intelligence. It's just strictly training the computer to recognize patterns. Okay, so again, we calculate our rho ratio, and this time just happens it's 1. Okay, so we calculate P0 again, and in this case, because rho is 1, then the P0 is the bottom formula here, which is 1 over n plus 1. Okay, once we have P0, we can calculate P full. Again, full is P4, and so rho to the 4 P0. Okay, and then rho for us is 1, P0 is 1 over 5th, so the probability is 0.2. So the Barber 1 has a 51% chance being full, Barber 2 has a 20% chance, so who's more likely to be full when you get there? Barber 1. Okay, so if you haven't signed in, so I'd like to give you some time to do your evaluation before we do the last model. So let's say I give you 10-minute break plus 10-minute evaluation. So we'll start up again at 4:15. If you are missing notes,